Hello everyone, I am Adya from Sri Venkateshwara College of Engineering from Department of CSE. Today I am going to give you all a presentation on understanding algorithms and efficiency analysis. Agenda. Introduction. What is an algorithm? Properties of algorithm. Space complexity. Time complexity. Best case analysis. Worst case analysis. Average case analysis. Order growth. Big O notation. Omega notation. Theta notation. Examples of algorithms. Conclusion. Introduction. Welcome everyone. Today we are going to talk about algorithms. Now, I know that words might sound intimidating, but don't worry, we'll break it down into simple terms and examples so that you can understand what they are and how they work. Algorithms are everywhere. They help us solve problems efficiently, from finding the shortest route to our destination to sorting through a largest amount of data. By understanding algorithms, we can become better at problem solving and more efficient in our work. So let's dive in. What is an algorithm? An algorithm is a set of instructions that tells a computer how to solve a problem or perform a task. It's like a recipe for a computer program, telling it exactly what steps to take in order to achieve a specific goal. Algorithms can be used for a wide range of tasks, from sorting data to searching for information on the internet. One example of an algorithm is a simple sorting algorithm that sorts a list of numbers in ascending order. The algorithm works by comparing each pair of adjacent numbers and swapping them if they are in wrong order. This process is repeated until the entire list is sorted. Another example is a search algorithm that finds a specific item in a list by checking each item one by one until the desired item is found. Properties of algorithms. Algorithms have several key properties that make them effective problem solving tools. One of these properties is input, which refers to the data or information that the algorithm uses to solve a problem. For example, if you were designing an algorithm to sort a list of numbers, the input would be the list of numbers itself. Space complexity. Space complexity refers to the amount of memory used by an algorithm. This is an important consideration when designing algorithms, as some problems may require a large amount of memory to solve. For example, if we are sorting a large data set, we may need to use additional memory to store intermediate results. One way to measure space complexity is to look into the amount of memory used by an algorithm as a function of its input size. For example, if an algorithm requires O(n) memory to sort an array of n elements, we would say that its space complexity is O(n). It is important to note that space complexity is not the same as time complexity, which measures the amount of time taken by an algorithm to solve a problem. Time complexity. Time complexity is a measure of the amount of time taken by an algorithm to solve a problem as a function of the size of the element. It is usually expressed in terms of the number of operations performed by the algorithm, such as comparisons, assignments, and arithmetic operations. For example, consider the problem of finding the maximum element in an array of n integers. A simple algorithm for this problem would be to compare each element of the array with the current maximum element, updating the maximum if necessary. This algorithm would take n-1 comparisons in the worst case, so its time complexity is O(n). Best case analysis. Best case analysis is a way to measure the efficiency of an algorithm by analyzing its performance when given the best possible input. It is important because it gives us an idea of the lower bound of the algorithm's running time. For example, if we have a sorting algorithm that is designed to sort a list of numbers in ascending order, the best case scenario would be if the list is already sorted. In this case, the algorithm would have a lower bound of O(n) time complexity, which is the best possible performance for an sorting algorithm. However, it is important to note that the best case scenario is not always the most common or realistic scenario. In fact, many algorithms have a worst case scenario that is much more common and should be considered when analyzing the algorithm's efficiency. Therefore, while best case analysis is useful, it should not be the only factor considered when evaluating an algorithm's performance. Worst case analysis. Worst case analysis is a method used to determine the maximum amount of time an algorithm will take to complete its task. It involves identifying the input that will cause the algorithm to perform the most tasks, resulting in the longest execution time. This analysis is important because it helps us understand the upper bound of an algorithm's performance, which allows us to make informed decisions about whether or not to use the algorithm for a particular task. For example, considering the sorting algorithm known as bubble sort. In the worst case scenario, where the input array is already sorted in reverse order, bubble sort will take O of n square time to complete. This means that as the size of the input array grows, the time taken by the algorithm will increase exponentially. By performing a worst case analysis, we can determine that bubble sort is not an efficient algorithm for large input sizes, and we should instead consider other sorting algorithms such as merge sort or quicksort. Average case analysis. Average case analysis is a method of analyzing the efficiency of an algorithm by considering the average or expected input size and input distribution. This type of analysis takes into account all possible inputs and their likelihood of occurring, which provides a more realistic estimate of an algorithm's performance compared to worst case or best case analysis. For example, if we are analyzing the efficiency of a sorting algorithm, we would consider the average length of the list to be sorted and the distribution of values within that list. One common technique for performing average case analysis is probabilistic analysis, which involves assigning probabilities to different input sizes and distributions. Another technique is to use statistical sampling, where a subset of inputs is randomly selected and analyzed. By using these techniques, we can gain a better understanding of an algorithm's performance under real world considerations. Order growth. Order growth refers to the rate at which the time complexity of an algorithm increases as the input size grows. It is a measure of how efficiently an algorithm can solve a problem as the problem size increases. For example, consider two sorting algorithms, bubble sort and merge sort. Bubble sort has a time complexity of O n square, while merge sort has a time complexity of O of n log n. This means that as the input size grows, bubble sort will take much longer to sort the data than the merge sort. In fact, for large input sizes, bubble sort becomes impractical while merge sort becomes efficient. Big O notation. Big O notation is a mathematical concept used to describe the upper bound of an algorithm's time complexity. It helps us understand how the running time of an algorithm grows as the input size increases. For example, if we have an algorithm that takes n square steps to solve a problem of size n, we would say that its time complexity is O of n square. The letter O in big O notation stands for order of magnitude. It represents the rate at which the running time of an algorithm increases with respect to the input size. The notation O of f of n means that the running time of the algorithm is proportional to f of n for large values of n. For example, O of n means that the running time of the algorithm grows linearly with the input size, while O of log n means that it grows logarithmically. Omega notation. Omega notation is used to measure the lower bound of an algorithm's time complexity. It represents the minimum amount of time required for an algorithm to solve a problem given a particular input size. For example, if we have an algorithm that can sort an array in n square time, we can say its lower bound is omega n square because no algorithm can sort an array in less than n square time in the worst case. Theta notation. Theta notation is used to measure the time bound of an algorithm's time complexity. It represents the set of functions that are both upper and lower bounds for a given function. In other words, it provides a range of growth rates for an algorithm's running time. For example, if we have an algorithm with a running time of n square plus 5n plus 10, we can use theta notation to express its time complexity as theta n square. This means that the algorithm has a growth rate of n square, which is both its best case and worst case scenario. Examples of algorithms. Sorting algorithms are used to arrange data in a specific order, such as alphabetical or numerical. Some examples of sorting algorithms include bubble sort, insertion sort, and quick sort. Search algorithms are used to find a specific item or value in a data set. Some examples of search algorithms include linear search, binary search, and depth first search. Graph algorithms are used to analyze and manipulate graphs, which are mathematical structures consisting of nodes and edges. Some examples of graph algorithms include Gregshaw's algorithm, Kroskal's algorithm, and Freud-Warshall algorithm. In conclusion, algorithms are a fundamental concept in computer science and play a critical role in solving problems efficiently. We have defined what an algorithm is and discussed its key properties such as input, output, definiteness, effectiveness, and finiteness. We have also explored the importance of measuring space and time complexity, analyzing best, worst, and average case scenarios, and understanding order growth and notations such as big O, omega, and theta. Furthermore, we have provided real world examples of algorithms and their applications in various fields and discussed the challenges in algorithm design and optimization techniques. By understanding algorithms, we can develop more efficient solutions to complex problems and improve our ability to reason about computational complexity. Whether you are a computer scientist, mathematician, engineer, or finance professional, having a solid understanding of algorithms is essential for success in our field. So, let's continue exploring the fascinating world of algorithms and discover new ways to solve problems efficiently. Thank you for joining me today on this journey through the world of algorithms. I hope you found it informative and engaging. Remember, algorithms are all around us, and understanding them can help us solve problems more efficiently. Thank you so much for watching. If you like the presentation, please do like, share, and subscribe.